Okay, so we were talking about strength of materials, and I showed a ratio analysis diagram for steel, and unfortunately I forgot my pointer. Okay, well, it doesn't really matter. If you look at the ratio analysis, this is just a toughness, a measure of toughness, which is dynamic tear energy versus yield strength. And if you look at this region right in here, you'll see that here about 180 KSI is where it starts to drop off, and your maximum up there for toughness is 10,000 foot-pounds. If I go to the same diagram for aluminum, it turns out your drop-off is at 40 KSI, and your toughness is 1/5 as much. It's around 2,000 foot-pounds. Your critical flaw sizes are going to be similar because that basically comes out of the geometry of the material and the yield strength, but if you drop the yield strength, then you'll get the same critical flaw sizes at actually it's a yield toughness ratio, so far as that goes. In any case, that's for aluminum, and that's why the guy, when I was a student or a young faculty member who was director of research at US Steel, used to call aluminum the near metal. It was almost ductile in his opinion, okay? It has about 1/5 the strength and 1/5 the toughness. If you go to titanium, and the reason we only have 3 ratio analysis diagrams, because this is what the US Navy was interested in building submarines out of back in the 1950s and 60s, when what's his name? Pardon me? Rickover? No, it wasn't Rickover. It was the father of fracture mechanics. George Irwin was head of mechanical engineering at Naval Research Laboratory. And he's considered the father of fracture mechanics because he took this idea that Griffith had that you could study the fracture of a brittle material like glass, and you come up with this. I put it up the other day. The fracture toughness is equal to the stress times the square root of pi c. That's the fundamental equation of fracture mechanics. Came out from Griffith in 1925. Everyone thought it only applied to brittle materials. Irwin showed it also can be applied to ductile materials. And so it's much more general than just brittle materials. It was originally, oh, I do have my pointer. All right, just looked in the wrong place. But anyway, so Irwin was trying to study this because of the Liberty ships after World War II, trying to understand it and how to apply it. And he found he could use the fracture mechanics formula of Griffith from 1925. This was 30 years later. He applied it to steels and titanium. If you look at titanium, you find you have about 1/3 the toughness of steel, and the strength is actually about 2/3. Okay, the drop-off here is about 120 rather than 180 KSI. So the materials have different properties. These are the only ratio analysis diagrams. You could do one for copper or nickel or something. Copper would have a very high toughness. It's a very ductile, malleable metal. It wouldn't have fantastic strength, but some copper alloys can actually go to about 200 KSI. I actually should have brought it. Anyone know what copper alloys go to 200 KSI? Beryllium copper, okay? You put a little bit of beryllium, get a precipitation, and you can get 200 KSI. And the example I have is just a regular old 10-inch adjustable wrench made out of beryllium copper, because you can get the same hardness as steel with only a little bit of a toxic metal. It's not toxic when you use it. It's only toxic when you breathe it, so that's not a problem. But you can buy a full set of tools, just like you'd buy at Sears out of steel. You can buy a set of socket wrenches and pliers and screwdrivers for $500. You can buy the same thing out of beryllium copper for $5,000, okay? Copper is a little more pricey. Why do you use beryllium copper tools? They use it a lot in the mining industry. Fatigue. Pardon me? No, not fatigue. Turns out spark resistance. Copper has better thermal conductivity, so if I took a piece of copper or if I had 2 pieces of metal, and one was steel, I took 2 pieces of steel and I bang them together, I could get a spark. You take copper even against a piece of steel, the high thermal conductivity won't generate the spark. You won't get the high temperatures because of the high thermal conductivity. And you don't want sparks in the bottom of a mine. where you could have a lot of gas and it could go kaboom and kill a lot of people. So for 10 times the price, you can get different strengths in different materials, but there are technological limits. And some of these diagrams, they actually call the upper curve there on this bending down curve the technological limit, okay, so far as that goes. We can also look at strength versus maximum service temperature of materials. And this is the Ashby plot. Remember, Ashby plots typically go over about 5 orders of magnitude, maybe 6 in both directions, okay? Sometimes 7, but usually about 5 orders of magnitude. And this is maximum service temperature. So room temperature, room temperature is back here, and you can see where foams and plastics and stuff are very good around room temperature. But if you want to go above 300 degrees C, which is not that high, but if you want to get up to a couple of thousand degrees C, you're really limited in the types of materials you can use. In fact, most metals can't go to 2000 C. They only go up to about, actually they don't go to 2000 C. They only go up to about 1000 C in operating temperature. And they tend to melt around 1200 C, most of the common ones, unless you get to refractory alloys. But the ceramics just keep on coasting, okay? Problem is they tend to be brittle, and that's a problem. So that kind of concludes the strength part of comparing strength, and strength has to be measured by 2 parameters. One is force, and the other is energy. Right, good, okay? Nobody knew that until 50 years ago when George Irwin came along, okay? Well, actually, the Liberty ships. And they still don't have energy in most of the codes. I mean, the civil engineers got it in the 1990s because of the Northridge earthquake. And they found that buildings built in the 60s, when we knew about the need for fracture energy, but it wasn't part of the code. It wasn't required, so no one's going to pay for it back then. And then you have an earthquake come along, and those buildings' connections just snapped. And it cost billions of dollars. And so the civil engineers decided, maybe energy fracture is important, okay? But there's still plenty of other industries where people still, until they have a big failure, many times they don't start requiring things. In fact, there's a guy who was elected to the National Academy of Engineering, same year I was, from Duke University, and he wrote a book, To Engineer is Human, and that's what made him famous. That he didn't do anything famous in engineering. He basically wrote a book about engineering and said that engineering progresses historically over thousands of years due to failures. We have a failure like the Tacoma Narrows Bridge, if you've seen Galloping Gertie and things like that. You have something like that, and people just keep on pushing the limit and pushing the limit until they push it too far, it causes a major failure, and then everyone says, well, why did that occur? Okay, and they start developing codes and standards to keep it from happening again. So now I wanted to go into something that's been used to bug me about 30 years ago, material substitution. And the example I gave back then, 30 years ago in a paper, was refrigerators. Okay, when I was your age, refrigerators were all made out of steel on the outside and enameled steel on the inside. Okay, might have been painted on the outside. It was enameled on the inside, because one of the steel's great Achilles' heels is its lack of corrosion resistance. But you can enamel it, and you would have something that was corrosion resistant. And then people decided that plastics would be a better material for the inside. They still keep steel on the outside of refrigerators and stoves and things. Well, stoves, you kind of need it because it gets hot. You start making stoves out of plastic and they tend to melt on you, okay? But refrigerators, you can make the inside out of something that has a low surface energy, so it's easier to clean. Things don't stick to it as easily with low surface energy. And you don't need strength on the inside, because if the little kid comes up on their trike and runs into it at full speed, the steel will resist the dents, but the plastic is on the inside and it won't break. It would break if it got that impact, because the energy of fracture of plastics is nowhere as good as steel. So nowadays we make steel outside and plastic on the inside. But what bugged me, because I lived through this transition in the 80s, okay? And I would go and buy a nice refrigerator, and within 3 years it was a piece of junk because they screwed the shelves into the plastic. Well, that's not how you design plastic, folks, okay? Plastic can't take screws, holes, and sharp stress concentration. It's a somewhat brittle material. I've shown you about fracture mechanics. You put a little notch in something and it breaks easily. Plastics don't have the toughness of steel. So if you're going to design a refrigerator, it turns out by the 1990s, KitchenAid and other people learned you slide the shelves in. You don't screw them in. Plastic has this wonderful property. It's easy to mold into complex shapes. So you mold a slot in there, and now you go look at virtually any refrigerator. It's made out of plastic, but there's no screws on the inside. The other problem with screws on the inside, after time, they would start rusting, and you'd have this little rusty drip on the inside of your refrigerator. It didn't look very good. Plastic is great. It's got great room temperature corrosion resistance, okay? They were putting in, they were essentially designing things the way they used to design things, and they didn't take this new material, plastic, on the inside and think about how do I design for plastic. And now there are handbooks that will tell you, you don't design plastic as if you were designing something like out of steel, okay? Steel has different mechanical properties than plastics. You work to the advantages of each material. So that's my little, and now I can buy refrigerators that will last for 15 years rather than falling apart in 3 years. There's a certain advantage to something that falls apart in 3 years. What's that? You get to sell more of them, okay, if you're the seller, okay? But it doesn't get very good reputation. And in fact, what car nowadays, among cars used by people in the United States, a common, car that sells a couple of 100,000 copies a year, what brand has got the highest reliability, typically? Toyota is usually up there, but Honda is also up there. Do you know why Honda has such a good reputation? Because in 1973, they came out with a Honda Civic, and it would rust through in 1 year. It had Honda got terrible reviews. No one would buy a Honda after 1973 because it was junk in terms of corrosion resistance. So the people at Honda said, we got to do something. And they did. They improved the quality much better than even Toyota in terms of corrosion resistance. And generally, Toyota is known for their engines. Their engines just will run forever, okay? But if you actually look at the body structure and everything else, Honda basically turned it around completely. They developed a terrible reputation in the 70s for the original Honda Civic, and now people don't remember how bad Hondas were. So they learned from their experience. So if we review some things we've talked about in structural materials, there are externalities in different things. I actually have one other externality to talk to you about. The number one driver in selection of a structural material is just cost. We use structural materials in very large volumes, in some cases billions of tons a year, and so whatever we use had better be cheap. And the cheapest material, crushed stone, is by far the largest use because it's the cheapest. Availability. Well, it turns out we also talked about that. And some things that are excellent materials, like nickel alloys, fantastic, except they're just not as available, okay? They cost 100 times as much as steel or 50 times as much as aluminum. Strength and ductility, we've talked about that. Ductility is a measure of toughness in some ways. It's not exactly the same, but it's somehow related. It's the ability to stretch and deform before something breaks, and brittleness is something that breaks before it stretches. So strength, ductility, and toughness. Stiffness, we talked about that. Lightweight, very important if something moves, and the faster it moves, the more important it is, okay? And we can look at why did I throw this one in? I don't know if I threw this one in or one of my assistants did. But you can look at different materials. This actually shows everything else unhighlighted, but polymers have a certain advantage in specific strength and whatnot. We can also look at toughness of things or stiffness of things can be a function of geometry, so far as that goes. Lots of different ways to look at things, and you have to look at what are the key parameters. And there's not generally one key parameter. There's probably 2 or 3 primary parameters for whatever your application is, and you pick your material based on that. Okay, any questions? Let me give you the one other one that I guess I didn't even know about until they redid my office a couple of years ago. And I hadn't really paid attention to what was going on. Usually when you put copper pipe in a building for a heating system or a water system or whatever, you would solder it, right? And then in 1978 you couldn't use lead tin solder. You had to get the lead out, and you had to start using tin silver solders, tin silver antimony solders. And they're okay, but they tend to leak a little bit more. But the real problem, the thing got expensive, is over time they had enough plumbers burn down buildings while they were soldering things that they started saying you have to have a fire watch. And then in places like Massachusetts, you ever notice we have policemen when they're doing work on the roads? That's actually a law in Massachusetts. This is something that helps keep the police from all going dishonest. They don't want to pay them enough to support a family in Massachusetts, so they allow them to do off-duty work and earn 45 bucks an hour by being someone to stand there while other people are doing construction. It's basically a tax on the construction process, but it also allows a good, honest policeman to make enough money to support a family. Otherwise, they're going to be tempted to keep some of that drug money and, you know, buy TV for their kids or something. Well, turns out the firemen wanted something good like that. So in the city of Boston, you got to have a fire watch. I mean, it says, and it's written into the OSHA regulations now, if someone is doing hot work, they're welding or they're soldering, anything that could start a fire, hot work, they have to have a fire watch. So in construction, this is one of the reasons construction, whether it's bridges and buildings or anything, has gotten so expensive because you generally have 2 or 3 people standing around watching one person work, okay? And one of the things is you got to have a safety watch when someone's doing hot work, and they're supposed to be looking to see if they got to put some fire out that started that no one knew about. Well, it turns out in Boston, that fire watch has to be a fireman. You have to be with part of the Boston Fire Department. And I don't know if they're getting 45 or 60 bucks an hour. But now one of your bigger costs is to pay some firemen to hang around for 8 hours one day while you got the plumbers doing plumbing work in the building because they're soldering things. So some guy came up with a bright idea to, and I don't have all the correct fittings here, but basically you got the regular old copper pipe, and for only 30 bucks you can get one of these fittings. Kind of pricey, but it's got an O-ring in it, and you buy a special tool for $800 and it will squeeze it together, and you make a mechanical O-ring seal, no hot work. So basically this is, if you have plastic tubing that would go inside here and they squeeze it down, and they've gotten rid of a lot of the hot work, and this is an externality of regulation, and it's specifically safety regulation. Get rid of the firemen, send them home, let him find some other way to earn money beyond his salary, because you're not going to pay him enough to support a family of 4 in Boston, okay? Anybody know what it costs to support a family of 4 in Boston, according to The Economist? $65,000 a year. Now, a lot of firemen make that much, but not when you're starting out, okay? Some of the better jobs for a lot of people will not ever get you to a living wage in the Boston area or San Francisco area. If you're in the middle of South Dakota, it might be a living wage. Well, actually, South Dakota is not a good example with all the fracking going on. Middle of Wyoming, $60,000 salary, you do quite well, okay, but not in Boston, okay? So there are other regulations that people come up with. So material selection examples, metals, moderate cost. They are more expensive than stone and concrete and wood. They have good strength and toughness and ductility. Ceramics, low cost, stone, concrete. They can have very high strength but very low toughness, and these are not the same, okay? Concrete in compression has very high strength. It has lousy toughness, particularly in tension, and it's brittle, okay? And glass is another material, very important structural material. There's not very many things that have the property that you can see through them, other than Harry Potter's cloak, okay? Polymers, moderate cost, low strength, low temperature capability, and low stiffness, okay? But easily formed, I should have put down more easily formed than the other two, because you can form at room temperature all kinds of neat ways. So there's different strengths and weaknesses of each material, and you can go back to the $1 Billion Club and see which ones are the most popular. Now let's talk about materials competition, okay? And the example I like to give is simple old food containers, or beverage containers actually, more specifically. And I have some here. I didn't bring in something of all of them. We make some cans out of steel. We make some cans out of aluminum. This is an all aluminum can. It actually has a different alloy at the top than on the sides, because you have to form this one by drawing and stretching, and this one you need some strength, and you got to be able to have the pull tab that works and stuff. There's certain advantages to that. And of course, here's plastics. There's glass, and I could have brought in I probably somewhere had a piece of glass in my office. But each one of them has its own strength and weakness. Not mechanical strength and weakness, but advantages and disadvantages to its use, okay? Steel has a problem of corrosion, so most of our beverage containers, 98% of our beverage containers are made out of aluminum. If you go to Japan, what will they make them out of? Steel. Why? Because Japan had at one time the largest steel industry. Now it's China. The United States had the largest one after World War II, and then the Japanese took it over, and now the Chinese are the largest steel producers in the world. And Japan would, because of politics, had all kinds of ways to keep aluminum cans out of the market. So they basically made beverage cans out of steel. And there's problems in joining of steel for cans and whatnot. But in fact, we still make some cans out of steel. Ta-da! A pineapple juice can. Except the top is made out of aluminum. Why? You need low toughness so you can do the pull tab out of aluminum. And you can put a little seal around here. The bottom is made out of steel, okay? But you also notice something else, and I compare these two metal cans. What do you see about the difference in those two?
The steel can's a simpler shape.
It's a more slender shape, okay? And why is that? That's because someone used calculus of variations. This was one of the problems they gave me as an undergraduate in one of my math classes. Calculus of variations to figure out what has the maximum volume to hold the beverage and the minimum area, surface area, for the material that I'm paying for, okay? And it turns out you take a Campbell soup can and it's just about perfect, okay, for doing the calculus of variations where you vary the diameter and the height, and you can, under certain constraints, and it gets more complex when you start mixing materials, but you can still, you know, the mathematicians just love this. You add another constraint, like I'm going to make this part out of aluminum and this part. Anyway, it turns out the steel being cheaper than aluminum, you want to use more steel for your outside area than you do for aluminum, so you make a slender can as opposed to a, the Sprite can is sort of about the same aspect ratio of height to width as a Campbell soup can, right? So why did we make a composite can out of pineapple juice? Corrosion, okay? Now, tomatoes are pretty corrosive, but aluminum is pretty good for the type of acidity we have with tomatoes. Although there are some tomato things that if you look on the inside, the aluminum is painted for corrosion resistance. So look at the cans that have a white inside, and now you know how corrosive your food is to aluminum. But it turns out for pineapple juice, it turns out the least cost when you consider protection against the acidity in pineapple juice and everything is essentially make a steel can, and if it's sitting upright on the shelf, then the bottom is steel and the sides are steel, and the top, the aluminum top, has got adequate because it's not immersed in it all the time. You don't get the pitting corrosion, okay? Different types of corrosion. So it actually makes sense, okay? Believe it or not. In the bigger cans of pineapple juice, what are they made out of? They're steel. Turns out they're steel. So pineapple juice comes, see, you never paid attention when you went to the grocery store, okay? There's lots of material science there. You could have, someone could have done a paper on that.
In
yeah.
one of our, I think 302 or something, we did a lab, and it turns out that the aluminum cans are pressurized, and steel cans generally never are.
Right.
Because the internal pressure is what lends the structure for stacking the cans.
Right. It turns out when they first started making aluminum cans, they were pretty thick-walled, and they weren't controlling the shape. The better example, the reason I brought this plastic bottle, look how thin this has become, okay? You may not remember it when you were 3 years old, but the plastic was a lot thicker, and they've been getting it thinner and thinner and thinner. Why? Because one of the problems with plastics, one, they're permeable, and the other is cost, okay? Things will actually diffuse through the plastic. I had a situation once where someone was interested. There was a big fire, and someone had a plastic gas can that was survived the fire, and they wanted to know how much gas had been poured out of this gas can into the steel tank or aluminum tank, whatever it was, of this machine. And they went back 3 years later, and the gas tank, the plastic gas tank, was empty. Why? Because all the gas had diffused through the wall of the plastic. It turns out it had been full, and someone had actually opened it up and taken a picture right after this big fire, and there was gas in it. And they sealed it and put it in storage, and came back 3 years later, it was empty. And originally, General Motors and Ford used to use lead-coated steel to make the gas tanks. Not zinc-coated. It turns out zinc-coated steel will be corroded by some of the things in a gas tank. But lead has excellent corrosion resistance, and they would use what's called tern, T-E-R-N-E, tern-coated steel, which is lead-coated steel. But then when they wanted to get lead out of the environment, they said, well, we'll just use plastic. So they started making plastic gas tanks, and the designers thought this was fantastic. The plastic could be molded, the steel had to sort of be stamped and formed, and you couldn't make it into these odd shapes that would fit into the little cubbies that you have around the axle and and stuff in your car. Whereas you could get more volume because you could mold this plastic tank. Anybody know how you would mold a plastic tank? It's like blowing up a balloon, but you blow it up into a form or a shape, and you take hot plastic and you blow air on it, and like blowing up a balloon into a form, and it takes on the shape of the form.
Is that blow molding?
Blow molding. It's called blow molding. Okay, it's just blowing up a balloon into a cavity that's got a shape to it. Well, the problem with that is the EPA came along and said, oh, we're losing 1% of all the gasoline in the country as volatile organic hydrocarbons into the air by just the permeability through all these 30 million cars with the gas tanks out there. And so they said, oh, we're going to stop that. we're going to put regulations on how much permeability you're going to have. So this was 25 years ago. I had a student working at Ford, and he was actually working on another problem on the paint line where they made the bumpers and the plastic bumpers and the gas tanks. But I went to see where they were now using a 7-layer composite. Okay, it wasn't just a simple balloon. It had 7 layers of different plastics, some of which were for strength, some of which were for permeability, resistance, but it was getting very, very complex. Okay, but in fact, they still use those plastic composites now for gas tanks on cars, and they have a low enough permeability. So people don't usually think about it, but you do have permeability, more permeability in plastics than you do have in metals.
Was there no coating they could put on, like just a regular?
Well, that's what they do with 7 layers, okay? It's easier when you're blow molding. You can make 7 balloons, you know, inside one another, and now you've basically got a coating.
If you could do like 1 layer of plastic, like coat it with something.
Well, if you start, and I'm not an expert on the gas tanks, but I know they ended up with 7 layers. To meet all the requirements, they had to go with 7 layers.
Right, the plastic might get softened, for instance, underneath the structure.
Yeah, no, they
Is that why plastic bottles with carbonation, like lose their carbonation over years? The CO2.
Plastic bottles, yes. The CO2 will diffuse out. Yep. And they make them thinner and thinner to get away from cost. You notice I didn't have cost up here. The two that don't have a cost disadvantage, okay, because these are the disadvantages, are steel and glass. Glass, one of the problems is weight. Now, people will tell you, beer purists will tell you that the best beer comes in, well, it comes draft, but the next best is a glass bottle as opposed to a metal can. Because beer is not very acidic, it's like 4.5 or 5 pH, but it has a little bit, and it will pick up purists, just like the wine purist. A beer purist will taste the difference, and so they like glass bottles. But when they build a brewery for the beer, which might be producing 8 million barrels, where do they put the glass plant? Right next door. Only a fence separating the two, because you can't afford to transport all that weight. And you can't just make glass bottles thinner and thinner because they're brittle. You have to still have a fair amount of weight, but they are considered for a number of things, like some medicines and things, the gold standard in terms of purity. Okay? Glass has low surface energy, doesn't pick up things, better than metals. It's going to last for 1 million years without decomposing if you do it properly. So plastics, permeability, and cost. I mean, I've shown you where the plastics, just the energy content of plastics is 5 times the energy content of steel and 2.5 times that of aluminum. So if you're going to use plastics, you got to blow mold it thinner and thinner, and you had mentioned the pressurizing the aluminum cans. Well, the aluminum cost twice what the steel cost. So you got to make the aluminum thinner, and what they did, in the 1980s, they were using supercomputers to design the aluminum cans. It's a multi-billion-dollar industry, okay? And they had to use supercomputers to figure out exactly how thin they could make it and still have enough impact resistance if someone drops it on the floor that it doesn't go shattering and leaking and everything. Composites, I should have brought, I do have some juice boxes in my refrigerator, some juice. And the juice boxes also have about 7 layers. And one of those layers is aluminum foil, okay? That gets around the permeability problem. You don't do that on gas tanks because you're going to blow mold them. But that makes a real problem for recycling when you got 7 materials that you've got to recycle. Whereas typically plastic, the milk bottles, or better than just talking about milk bottles, let's talk about the soda bottles, okay? Which they also have gotten so thin. Some of the cheaper ones, you take the top off and it's no longer pressurized, and you try to pick up that 2-liter bottle and you can't do it because it collapses on you, right? You don't have the pressure holding. When it's still got pressure on the inside, it's easy to pick it up. It doesn't collapse on you. But it's the pressure that's giving it the strength, okay? Basically, when one material in the food beverage business gets a little bit of an edge over some new increase in technology over the other, then the others will start doing things to get better. And we use virtually all materials for beverages. And so it's not something I can just tell you at a 40,000 foot level. You should always use aluminum for beer cans. No, if you're a purist, you should use glass, okay, for beer. But it's a big deal. I remember a year and a half ago, one of the breweries was advertising, I think it was Coors, that they had plastic beer bottles, okay? Well, they had to do a lot of work, make sure you didn't taste like plastic, okay? The plastics are more permeable, and anyway. You also have to make sure you don't have any monomers left in that plastic that all of a sudden the EPA is going to, or the health people are going to be all over you. So anyway, it's a pretty mundane material to think of just beverage containers, but it's a tremendous volume, and you wouldn't believe the technology that goes into these things because it's a big business. And saving a fraction of a cent on 1 billion bottles a year turns out, talk about that, 1/10 of a cent times 1 billion, that's $100 million. So anyway, volume has its advantages. Selection or competition among materials for conveying water. In the old days, well, the oldest days, they would just dig a trough in the ground and they'd let the thing kind of come through the ditch, and the water would just the water would just kind of go through until you had a muddy ditch. Then they learned they could heat up their clay and make pipe. And so here's a clay pipe from 4000 BC. The Romans used concrete and stone to make aqueducts to transport water. Back 100 years ago, or 150 years ago even, we were using cast iron pipe and then steel pipe to transport water. But that had a problem. So now people go in and they actually put a little layer of concrete on the inside of the steel pipe to keep it from corroding from the inside. Could still corrode on the outside, but you can protect that with cathodic protection. But now people like to use plastic pipe, and you can see the rubber O-ring in there, okay? Just like these other fittings. The rubber O-ring. Concrete pipe, particularly for large diameter pipe. And we used to actually even use wood, okay, as far as that goes. Virtually every material has its strength, but for water that's going to flow through there, it's not going to be stagnant. It turns out plastic is the advantage right now. If you're going to convey gas, it turns out we started out in the old days with a wooden pipe. That is a wooden pipe from 1840. They would just take an old tree and they would gun drill the inside, lay it in the ground, and transport gas from whatever their source of gas was. And originally, most of this was for the utilities for street lights in the cities, okay? And I have seen things when Boston Gas, it's now National Grid or whoever it is, but when it was called Boston Gas, I've been down to their training facility down in Norwood, and they have examples where they digging in the ground and they find one of these old wooden pipes from the gas lines from the 1800s, okay? Or one of the cast iron pipes. I have some pictures of the cast iron pipes somewhere. But then people realized that wood didn't have a very long lifespan, maybe 20 years, 30 years before it rots. And so people started using cast iron. And we use cast iron for water mains. One of the biggest problems in most of the cities, like Boston and New York, is we got 100-year-old cast iron water mains, and every now and then one of them breaks, okay? And they're so brittle that when you work on it in this block, you know that about 5-10 years down the road, the next block is going to have a leak. Because in New York City, when you go and dig up the road to replace the pipe that broke, you're going to disturb the pipe on either side. And you don't want to have to dig up a long section of road in New York City It tends to disturb traffic, okay, for too long. And it helps me a lot. You know, when I get a job in New York City, they say we had a water pipe burst. I said, when was the last one in that area? And usually you find there was one about 3 to 5 years earlier. Okay. About 5% of all the water distributed in the United States, potable water, is lost through leaks in the pipe due to corrosion and other things. Okay. I have a strip, my house is 80 years old, and I had some construction done on it. And this spring, when the grass came up, the water line from the street into the house, the grass was growing great, even though I wasn't watering it, because the line underneath is leaking so much, okay? Now, that's the town's losing all that water. Once it gets beyond my, my foundation, now there's the meter, and I have to pay for that. But the town is just, everybody knows that 5% of the water in distribution is lost through leaks. That is also true in gas pipe, okay? About 5% of all the gas we distribute in this country. And we've got, you know, something like 500,000 miles of major pipe for oil and gas in this country, much of which is 60 to 70 years old and is corroding big time. So what have people done? Back in the 1980s, the American Gas Association decided the solution was plastic. And so this is a piece of gas pipe. How can I tell it's gas pipe? Anybody know? It's got a yellow stripe. Pipes carrying flammable gases are supposed to be color-coded yellow. This is a piece of stainless steel gas pipe with a plastic coating on the outside, but it's stainless steel on the inside. I won't pass these around today. I can pass them around later, but most of the gas pipe that's been going in for the last 30 years is thermally welded plastic pipe, okay? And when my gas pipe at my house, 20 years ago, they go and the regulators make them sniff. They put just stick a probe down in the ground, and they have to do that about once every year in an older neighborhood. A newer neighborhood, they may not have to do it, but once every 3 years, once every 5 years, to find the gas leaks. And as I told you, 5% of the gas is lost to distribution. When it gets really bad, like last winter while my house was being worked on, my wife and I lived at my son's house because he lives in the same town. And I was noticing this gas smell when I get up early in the morning to come in. And it turns out they finally got around to fixing the gas leak. They knew it was there, so we didn't have to tell them. We told them, but we're smelling gas. And I would smell it early in the morning because the sun's not out, not a lot of wind at night, and so I would smell it first early in the morning. And they just fixed it about 3 weeks ago. Okay, that gas leak. That one crew has 1,700 backorder leaks to fix. And it probably takes 1 or 2 days to go fix a leak. You got to dig a hole in the ground, find the leak, okay. So, job security for, anyway. So, we use a lot of different materials. This other one down here is corrugated stainless steel tubing. This is another thing that the Gas Association came up with in the 1980s. It wasn't really approved for residential use until 1997. The problem with this, it's got the yellow coating on a corrugated stainless steel, and if you have lightning come through, like if you live in Florida, which is Lightning Alley, Florida has a higher density of lightning strikes than any other place in the world. It's surrounded by water that forms clouds that form lightning, thunder and stuff. You get hit by lightning and you can perforate this, and now you have a flamethrower in your wall and it burns down your house. Okay? I've got over 100 cases of houses that have burned down. And you know what? I kept on looking at these houses. I thought, how come these people live in such nice houses? And then I realized rich people build their houses on tops of mountains. And where's the worst place for getting a lightning strike? And don't believe this thing that lightning never strikes twice in the same spot. It does. Okay? And, I mean, anyway. So there have been some problems with corrugated stainless steel tubing when you go switching to different materials. The advantage is it's flexible. They sell it for about $5 a foot, okay? This old carbon steel pipe, black iron pipe, they sell for about 90 cents a foot, okay? This goes for $5 a foot. The advantage is a plumber takes 3 days to plumb a house, a brand new house, typically with this stuff. They have to thread it, they have to cut it to length. This stuff, you just put a fitting on the end and you can run for 100 feet with no connectors in between. It's flexible, bends around corners and stuff. A plumber can plumb the house in 1 day. So the company that's selling this is making a very large profit until they have to pay for the house that burned down, which that cuts into their profit. But they're still profitable enough that they have been paying them off.
It's corrugated so that it just like
Yep,
crumples. And then
bends.
plastic, bending of the steel.
That's plastic bending of the steel, but as a bellows, okay, corrugated bellows, you can bend it more times than it will ever see in service. It doesn't fail by fatigue. It fails because the lightning hits it and goes to ground and whatnot. So very interesting physics in it, okay, of lightning strikes and where it goes in a house, and no one can predict where it will go in a house. They've tried. They've run tests in Germany and in Florida. They've built homes and instrumented them and then triggered lightning. Sent a little rocket up with a little wire on it into a thundercloud and get the lightning to hit the house because you got a wire running back down to it. And then monitor where the lightning went, and it's nowhere near where the physicists and electrical engineers had predicted. So lightning is very unpredictable. Okay, so I'll see you, well, I won't see you anymore this week. Brian or Simone, Dr. Belmar will be lecturing the rest of this week every day. I'll be back next Tuesday. Actually, I'll be back next Monday, but Dr. Belmar's got next Monday too. Okay, thanks. Anybody have any questions?